Let me give you a brief video that describes how to use this worksheet to compute parameter estimates for the signal detection model. So what I have here are the data from the FBI Noblest black box study for the value for identification trials. And so you'll recognize this data because it has 6 erroneous identifications and it has an exclusion rate of about 7% here. And what I've done here, I've summed up the number of mated pairs that all of the examiners saw and the number of non-mated pairs that they saw. And then in this table right here, I've computed the proportions. So this is the 0.1% of erroneous identifications. This is the 7.5% of erroneous exclusions. And this is simply done by taking each one of these and dividing by the row total there. And then here are the predicted proportions from a particular signal detection model. Now that model is shown right here. So we have the evidence axis right here, where being on this side is more evidence in favor of identification or common source. And lower values here are evidence for different sources. And the way that signal detection theory works is that the non-mated distribution, which is this curve right here, the blue curve, that's just fixed at 0 and has a standard deviation of 1, so a spread of 1 here. And in this particular model, we're allowing the mated distribution here to have a different standard deviation. That's very common in signal detection theory models to allow that to happen. And we also include a exclusion criterion here and an individualization or identification criterion. I don't know why I used individualization. Clearly it should be identification. So in the middle here, these are the inconclusives, these are the identifications, and these are the exclusions. All right, so these numbers right here, these are the parameters that are associated with this. So if I change this number from 3.4 to like 2, you'll see this orange curve right here shift as I hit return. So it shifted to the left. Likewise, if I were to change the ID criterion to something smaller too, like 2.5, you can see it will also shift there as well. Now, in addition to this graph changing, you can also see that our predictions are changing. So this used to be 0.01, and now it's 0.06. Likewise, this used to be 7.5% error rate for erroneous exclusions, but now it's like 30%. Well, clearly that's not right. And so the way that this game is played is that you want to try to adjust the mated mean and all of these different parameters here so that you get numbers in the predicted proportions that are as close as possible to the actual proportions you observed in your data. So if I increase the mated mean to like 2.5, we should see some things change here. So this is the correct identification rate currently is predicted to be about 37%. It should be about 61%. If I change this mated mean to 2.5, you can see that the number jumps from 0.3, whatever it was, to 0.5. So we're getting closer, so I can try different numbers, 2.7, and we're getting closer there. But notice other things are changing as well. So this erroneous exclusion rate is dropping as well. If we go up to 2.9, we can see it's dropping as well, which it should, and this is getting closer and closer to here. So the problem for us is that there are many numbers, there are 4 different numbers that could change. And so rather than us hand tuning this model that we have just been doing, we can actually ask Excel to do it for us. So the way to do that is first you have to ensure that the Excel solver tool is present. So you go to Excel add-ins, and you can see that if the solver add-in is not checked, you can check it there. It should be built into most newer versions of Excel. So we'll click OK there. I'm not sure actually where that is in Windows. It may be under like the options or preferences window there. or menu item. Once you have the solver installed, you can go to Tools, and you go to Solver under the Tool menu. And the way this works is that we're telling it to change a bunch of variable cells such that we maximize the likelihood. So let me close this for a moment and talk a little bit about the maximum likelihood here. So as we get numbers in our predicted proportions that are closer and closer to our actual proportions, this likelihood value will get bigger. That is, it'll get closer and closer to 0. So if I change this from 2.9, for example, to 2.97, or let's do like 3.2, then this number here will get closer to 0. So it was minus 2920, so whatever it was, and now it's 2918. Likewise, over here, our blue is our ROC curve, and I'll explain what that is in a minute, from our data. And the orange curve right here is the ROC curve for the theory, and they're getting closer and closer to each other as well. So what we want to do is adjust these values here to make this number as close to 0 as possible. So if I change this to like 3.5, I don't remember what this one was. Let me do it again. 29, 18, 3.5. So it got worse there, so I went too far. I might be able to fix that, though, if I change the ID criterion. I forget the actual values. I'm going to cheat for a moment and see, remember what it's 2.9 and 3.4. So if we change this to 2.9, then this should get better, and it did. Okay, so this is very complicated to try to change these values by hand. So instead, what we'd like to do is ask Excel to do it for us. By the way the maximum likelihood works is very simple. It's a complicated concept that actually turns out to be very simple. The idea is that we want to figure out how likely is it that we would observe a sequence of respondings, essentially what we measured here, given a particular model. That's the likelihood ratio. It includes these kinds of things. What's the probability of observing data given a particular model? Well, the signal detection model plus these parameters, that is a particular model. It's an instance of a model. And if we change these parameters, it's another instance, but the assumptions that go into it, the assumptions of normal distributions, and the fact that there's an evidence axis, and you can partition it using these decision thresholds, all of that is the theory. So what we'd like to do is we'd like to figure out how likely is it we would observe this data given this particular model. Well, the model is essentially giving us these predictions. And so if we want to know how likely is it we would observe 6 individual erroneous exclusions, all we have to do is take 0.002 times 0.002 times 0.02 times we do that 6 times. And that's because what we're doing is we're saying in the data we saw 1 erroneous exclusion, and the likelihood of that, the probability of that is 0.002. And we saw another one, and the likelihood of that is 0.002. And we saw another one all the way up to 6 of these guys. And the fact that I'm saying and the fact that these are all independent, that is the examiners were each working independently. They weren't sharing information, so these are independent samples. The fact that they're independent means that we can multiply the probabilities. That's what and means in that equation. So we've got 0.002 times 0.02 times 0.02 times 0.02, and we keep doing that. And the same thing for these other cells right here. So we would take 0.652, and we would multiply 0.652 times 0.652, 0.652, 3,663 times. Now, it turns out that that gives you very, very small numbers. And so oftentimes what we do is we take the log of the probabilities here, and we multiply that times the number of items. Essentially, this log here allows us to add instead of multiply small numbers. And by adding them up, adding up log likelihoods as opposed to multiplying regular likelihoods or regular probabilities. I'm using the two equivalently here. We don't run into issues of very, very super small numbers here. Okay, so technically this is not the likelihood, this is the log likelihood value right there, which is why it's negative. Likelihoods can't be negative. Okay, so what we want to do is get these numbers, get these predictions as close as possible to these observed proportions. And it turns out that the way to do that is to maximize the likelihood. That is the best we can do in terms of getting this number as close as possible to 0, essentially is to get these proportions here as close as possible to the actual proportions. That's just the way that maximum likelihood works. And so we're going to ask Excel to do that for us using Solver. So what we're going to do is go back to the tools here and go to Excel, or go to Solver. And we're going to set our objective cell, this likelihood here. It's already selected, but we can click on it. Click on it right here. And then we're going to change these cells right here. So we're going to select these 4 cells. Those are the parameters that can change. And we want to maximize our likelihood here. Sometimes you minimize it, sometimes you want to set it to some other function, but we're going to maximize it. And so we're going to click solve in a minute here, but let's remember our likelihood here, minus 2870. And so I'm going to click solve. And Solver says it has converged to the current solution. All constraints are satisfied, so that's good. Usually you get that with this because it's pretty well behaved. And so I'll click OK and note a couple of things. First of all, our predictions are very, very close to the actual proportions here. Almost identical. They won't be exact. Well, they may actually be exact in this situation, except for rounding error. Also notice that this number here got closer to 0. It was like, I forget exactly what it was, but this is closer to 0 here. And notice that these numbers here have changed, and that's because those are the numbers that Excel adjusted to maximize the likelihood right here. So that's the way that this works. If you want to fit a different data set here, all you have to do is type in some different numbers. I'll go over to my sandbox here so I can play with it without messing up the other stuff. And let's just say we give a test to some examiners and we have like 6 erroneous exclusions and 10 inconclusives and 30 individualizations. And in another one we get, I don't know, 35 exclusions, 8 inconclusives, and let's just say 1 erroneous identification here. Okay, so we have a new set of data, and you can see that our parameters aren't very close at this point because our ROC plot, the data is in blue, and the theory isn't really very close to it. So let's go ahead and change these parameters to figure out how good this subject is. So what we're going to do is go to, oops, I forgot the data. Oops, it's under Tools, Solver. It's already set up here. These are already set up. So we'll click Solve. And there we go. So this gives us a measure of how good this subject is. So basically the D prime value that's shown down here is sort of a measure that allows us to decide which examiner is better at separating mated from non-mated pairs, regardless of whatever decision thresholds that they have or decision criterion. And otherwise, this model is doing a very good job. Actually, it has to do a good job because it has the same number of parameters as degrees of freedom here. It turns out that this data has only 4 degrees of freedom here, because if I tell you there are 46 total trials of mated pairs in the experiment, and there were 6 erroneous exclusions and 10 inconclusives, you can figure out that there were 30 individualizations in that. So basically, there are just 4 numbers that can change in this experiment from each subject, given the 46 mated and 44 non-mated trials. So that means there's 4 degrees of freedom, and there are 4 parameters here. So that means the model has to do a really good job. Doesn't mean that we reject the model. It just means that it's difficult for us to assess how the goodness of fit in the model. So that's the way that you use this particular tool to compute 2 things. One is you can compute how good the examiner is, and that's found in this D prime calculation. It's also sort of a combination of the mated mean and the standard deviation. But the other is to think about how conservative the examiner is. So let's change this a little bit. Remember, our ID decision criterion is 2, and our exclusion is about 0.8. If I have an examiner who makes more inconclusives, so let's say they make 4 exclusions and 12 inconclusives, and they make 30 here and 12 of these. Now if we go through and we do our solver, watch as I click solve here, watch these curves, sorry, the decision criterion, they should get closer together. So I'll click solve, it's gonna think for a minute, and when I click OK, it will move these closer together in theory. Oh, maybe it didn't change very much, or maybe it's already updated. Hard for me to tell. In theory, this exclusion criterion should have shifted to the right, to the left, to allow for more inconclusives here. Okay, so then essentially that's the way that this program works. You're welcome to use this to compute the parameters for any particular data set or any particular set of proficiency tests. And it's just a way of sort of separating out how good an examiner is at separating mated from unmated pairs from how conservative they are in terms of where they place their identification decision threshold. And that's the way this works. So feel free to contact me for more information about how to use this. Otherwise, I think it's a very useful tool.